Our final project is anomalous semiconductor detection via deep decision making. We hope our model can tell how it decides an anomalous image. We use deep neural network to extract features from input images and feed this feature to decision tree model to give final prediction. As a summary, we treat anomalous detection as binary classification problem. We classify semiconductors by making a sequence of decisions using deep features. To achieve this, we explore the combination of deep learning and decision tree model. The first speaker will describe unsupervised decision tree model. The second speaker will describe supervised decision tree model. In our unsupervised experiments, we use pre-trained CNN to extract features from semiconductor images. We then employ unsupervised decision tree to classify whether an input image is anomalous or not.
We used 3 unsupervised anomaly detection methods, including k-means, one-class support vector machine, and isolation forest. Among all of them, isolation forest performed the best. Here are some basic ideas about isolation forest. It is based on decision trees, for example, random forest. The difference between it and other random decision trees is that it explicitly identifies outliers instead of profiling normal data. During training, the first step is to sample the training data according to the given training ratio. Then, it iteratively builds binary decision trees until all data are isolated. During this step, it firstly selects a feature randomly. For example, in this picture, X and Y axis represents 2 feature dimensions. Then it chooses a random partition value between maximum and minimum values of this feature. For example, these are the partition values which have been chosen. We can see that because outliers are fewer and more different. For example, in the right picture, therefore they can be isolated more quickly. Thus, in the tree, the path to the outliers will be shorter. After building the forest model, we can calculate the anomaly scores to determine whether a data point is an outlier or not.
We did not obtain very high accuracy for unsupervised methods. We believe the reasons are twofold. First, we did not use any label. Second, the pre-trained recent features may not be discriminative enough for unsupervised learning. We then switched to supervised decision tree model to achieve high accuracy. We employ deep neural decision forest model. In deep neural decision forest, a CNN is used to extract deep features from input images. These features are fed into decision forest to give final prediction. In this model, every split node will route the input with a probability to its left and right subtrees. The final prediction is the weighted average of all leaf nodes. The weight of one leaf node is computed as a probability that the input arrives at the corresponding leaf node. For example, for leaf node 4, its weight is determined by the 3 split nodes along the path. The training of neural decision forest is an alternate process. There are 2 types of parameters in this model. The CNN parameter is theta, which is used to compute the routing probabilities, and the leaf node parameter is pi, which is used to give the final prediction. During the training, we first fix pi and update theta by gradient-based algorithm, and then we fix theta and update pi by finding the global minimum of the loss function. We achieved high accuracy using neural decision forest for the in-class Kaggle competition. But beyond the accuracy, we can trace and visualize the decision-making process of neural decision forest. Please visit our GitHub repository for more details and feel free to play with the code. Thank you.